Hey all, this is Dave Ward, Technical Sales with ImpulseRadar. We'd like to thank you for joining us. We're just going to give some stragglers 1 or 2 more minutes to join the meeting, and then we'll get started. For those of you that are already here, I will be helping Matt, our president, run the slideshow. Zach Pace, my colleague, is also here. He'll be running the chat. So we have everyone's microphones muted, but if you do have questions that pop up throughout the presentation, please feel free to make use of that chat feature, and Zach will get those questions answered. Again, 1 or 2 more minutes and we'll get started. Thanks. Hello, everyone. For some of you that have been here a couple minutes, hello again. Dave Ward, Technical Sales with ImpulseRadar. I'm here with Matt Wolf, our president. He's going to be the primary presenter today. We also have Zach Pace, my colleague, who will be running the chat. So you guys are all muted, but if at any point you do have some questions, please feel free to throw those up in the chat. Zach will answer them as we go. Additionally, when we get to the end of the presentation, we will open up the floor for some Q&A. So with that, we're going to go ahead and jump over into our slides. And Matt, you can take it away.
Sure. Hey, thanks, Dave. Thank you all for attending. Just a couple of announcements before we get started. We do have a couple of persons that'll make a couple of comments in the webinar. One is John MacArthur. He's pretty much the Chief Revenue Officer at Whisper Systems. And Calvin Platt from Pix4D, I just saw a message from him. He's having some technical issues, but I wanted him to speak just a couple minutes, both the gentlemen, a little bit about their companies. This presentation is geared to be educational. That's kind of our modus operandi. This was actually a seminar, or excuse me, a presentation I gave initially at the Subsurface Utility Engineering Association meeting. And I know some of the people that signed up have been there. So welcome back. Sahar Kamalu she was an intern that we engaged here at ImpulseRadar last summer. She normally would be co-presenting, but she couldn't be available today. She's finishing up a PhD at University of Oregon, or Oregon State, excuse me. And she was instrumental in helping us pull all of this concept together to integrate our leading underground subsurface utility engineering imaging tech, the Raptor, with some of the advancements that have occurred with LiDAR and photogrammetry. So that's the core, and what we designed the presentation around. If you look at the outline, it really is about how we learned that you can integrate these tools to help our customers that use the underground information to with their workflows and enhance their capabilities for deliverables. So that's pretty much the tenets and the let's say the philosophy behind how we presented this. So what the objectives were, and then this is strictly sticking with subsurface utility engineering. I have a background in it, both as a consultant, and now we work heavily with a lot of companies, obviously the team here. But years ago, I do remember sitting on the hood of a truck or leaning on a hood of a truck with colleagues, and we were using colored pencils, and we were kind of trying to get some kind of field data put on paper so that the CAD techs and 3 months later, when you're out of the field, you actually had some records of what you did, because as everybody knows, those paint marks will be gone, and especially in roadways, grassy areas, and they're gone. And if you've mowed 6 hours to a site, you're certainly not going back and redoing everything. So it was kind of a cumbersome way. And of course, with photogrammetry on the ground, you could take pictures and do all this other stuff. But the reality is, by using some of this, let's say, reality capture from a drone and some of the tools that are available, you could actually revisit the site virtually, and we'll prove that to you here in a few minutes. And it's really powerful. So there is no ambiguity. We also, back in my consultant days, I remember the CAD person can't see visually really the scenario of the hydrant, the pull box, and everything around it with all the marks on the ground. And if you didn't have a survey team come in and put a lot of discretization on some of these marks, they could jump over with a point in the data that's output, and it could be erroneous. So this was all kind of a mix of experience from my past, and then obviously we get a lot of input from our customers, which is our best resource always. So what we tried to do or attempted to do successfully was, how do we pull all these different tools together? And the three primary tools were LiDAR on a UAV, camera system on a UAV, and of course our Raptor underground imaging system. So I'm not going to go through every box here, but obviously you collect the data, there's some processing and pre-processing, and then we get to what we want as a deliverable. And I will say, for the SUE industry, what we found most useful for workflow and interpretation of our data, not the complete digital twin, but our data, was the photogrammetry, which was a really kind of a surprise to us. But to be able to have an orthomosaic and a high resolution available full time at any time you want to revisit the site was tremendous. So that was a big upside surprise for us going through this process, as a consultant would. So we decided to not just do this in a random way. We did it as if we were a consultant, as a SUE provider. So there's an abandoned grocery store site here. If anybody's seen the movie Driving Miss Daisy and you're not from the South, there are Piggly Wigglies. It is a grocery store. There's not many left, but there's an abandoned one. In 2003, it was in use. And in 2019, all the buildings were razed. So it's been a kind of a brownfield sort of, when I say brownfields, it wasn't contaminated as far as we know, but abandoned site, perfect for a redevelopment project. So we went through the historical imagery, and it was kind of fun. Before all the buildings were, this one little building off a little bit from, it was on the site, but it was raised eventually. I'm pretty sure that's a GCP, a ground control point for a high altitude ortho, probably imagery for the county or something, because that's definitely a cross. And there's a north arrow just painted on the top of that building. So that's the background of the site. And we've had access to the site because it's just kind of there. Just to go run the Raptor and do some testing and so forth. So we decided, let's do a full-blown simulated SUE project on that site. So turns out that public records, there is a plan for the site. So this is a classic. You have an abandoned site, you have a bunch of facilities in the ground. And I'm sure, and I don't know who, because there are marks there, there was a SUE provider, I'm sure, that came into the site and said, hey, here's your roadmap of what's here and how you can do connectivity for the new development. So I'm sure there was some activity to that effect, but it will be redeveloped. So this is a classic scenario of a SUE project under ASC 38, which is now 22. And I won't go into ASC. I assume most people here know what that is. When you get into our tech, for those on the call that may not be familiar, we have the Raptor array. It really has been a game changer for mapping large areas and small. We have several customers now globally, and the concept is that we can actually hook this thing up to the Raptor, any vehicle. We can collect data at highway speeds, or we can use a push cart for smaller areas, but the efficiency is unmatched. And it's not for every site, but we like to say for a congested corridor, streetscape, downtown, industrial, or redevelopment site like the one we picked, it's the perfect tool in terms of efficiency from the GPR side. And I will end this process with saying that we don't just use radar. As everybody knows, it's part of the tools in the toolkit under the standard. If you're not familiar with the Raptor, the novel part of how the Raptor works, we transmit and receive in what we call a herringbone pattern. So we get polarizations both ways, meaning if you're familiar with 2D GPR, you're pushing a GPR system and you get a nice hyperbola if you're perpendicular to that particular facility underground. And then typically you want to go both directions with an antenna to verify that it's not just a point diffractor and it's an actual linear object and it's a utility. We don't have to do that. We can run the Raptor straight down the road or a parking lot or whatever. And it's if we're running 18 systems at the same time, and it really isn't, because we're doing both polarizations. So it's a dense array basically. Oops. I think I skipped. No, I didn't. Okay, so if you saw picture on the left, that's a typical, scenario of a 4-lane. You can drive the van or whatever vehicle at any speed you wish, up to the speed limit, obviously. Just to be clear. And then the Raptor's adaptable. We've had it on ATVs and John Deere tractors, and you know what? We've got clients that probably done things we have no idea what that's been pulled with, but it's pretty adaptable in that respect. You have your positioning system, your GPS, or in some cases could be a total station if needed. But that particular picture with Zach on it, with John Deere, was an archaeological site. It's like 4-acre field, I believe, or something. And this was the best thing they had available. So why not get on a tractor? So just a little background on how the workflows on a Raptor system works. If you're driving up and down the road, there's two things you want to see. One is what you've covered already. So we have a moving map, obviously, background map to show you where each swath, those little rectangles in that picture of the Talon software, is your moving map. Each one of those little rectangles is the width of the array behind the vehicle driving up and down the road. And then most people that are collecting data absolutely want to make sure they're getting data. So you can toggle between the screens and you can see the raw data coming out of, there's a 12 channel at the top, so it's a little confusing, but it's an 18 channel system is standard. You can see the data scroll as you're collecting it down the road. And this is pretty much what you're going to see. If we don't have satellite background imagery up, which to me is a waste, but we have a moving map, and we can see that the little red triangle is the van. And we're going down Savannah Highway. This is literally at 60 miles an hour. We're going down Savannah Highway and we're collecting data. And then the commensurate thing you're going to see when you're going down the highway is the data scroll through. And if you've never seen data scroll at 60 miles an hour, this is what it looks like. And I have to admit, when we developed the Raptor and we first got into this, it took me a long time to figure out that this is actually even happening this way from having years of walking on a radar system at walking speed. Workflows, once you collect the data in the field, we want to QC that data right away because a lot of projects are not in your backyard. The Raptor can be moved anywhere in a vehicle. So if you're 3 hours from the office, we want to make sure you have good data integrity before it gets into the processing phase. And we also want to make sure we have, the main thing is the positioning, and all of that was copacetic. So you can immediately see top views within the same tablet or laptop that you collect the data in of your whole project site. We can filter out some GPS points that may be erroneous, that don't meet the criteria of fixed quality 4. There's numerous things you can do in here, but in general, it's a QC tool to clean up the data. But if you see this top view, which is roughly about a meter down, you're verifying not only did I get good data, but I also have good positioning, because when you see those laterals going across the road and they're perfectly lined up, then you know the GPS positioning system was stitched together beautifully with minimal error. And just, we're not going to go through the processing ad nauseum, but our ultimate processing deliverable or output that we can do is what we call Osprey view. These are just 3 examples from around different parts of the North America. And the concept is we can filter out the background scattering noise and other things we don't want to see with Osprey view. So we have a top-down view from the surface all the way to the detection limits of the radar. So the blues would be your maximum depths, which are hard to see probably on your screens, but we have a color code of yellows would be the surface, greens would be about halfway down through the section, and then the blues would be the deepest. I know in Vancouver that valve assembly, blue valve assembly, is over 3 meters down, and it's in blue. I'm not sure about the other depths, but all of these data are down to somewhere around 10 or 12 feet. And obviously for radar, this is really good conditions. So I'm going to turn over John MacArthur. I believe Dave has to give him a little nudge here with the software. I'll let John. You just let somebody else in. Let somebody else.
I'm here.
Oh, John. Okay. Did everybody's mics turn on?
I don't think so.
John, do we have you?
I was able to just turn it on.
Okay.
So
All right, well, here,
quick,
John
quick and easy.
MacArthur
So
from
thank you
Whisper.
so much for having me. Yeah, thank you, Matt, and team for having me on this call. It's exciting to work with you guys. I mean, you mentioned it earlier. The best feedback you get is from your customers, and so one of the reasons we were so excited to, kind of win the Impulse Radar American Drone Sweepstakes. I feel like we, because I know you looked at a lot of options, but learning more about your use case and all the things that your customers are doing and how they're using the data and the types of missions that they need. That's all the feedback that we need in order to make our systems the most user friendly out there. So real quick on Whisper, we were rolled out of a startup accelerator at Mississippi State in 2017, and we've been very focused on the surveying and mapping and inspection industry for the last like 4.5 years. We've purpose built our systems specifically for that with the mission planning, the fail safes, and then the partners that we have chosen on the payload side. So we've got high resolution cameras, and I'm losing track of the amount of LiDAR units that we have been integrated on. So it's the Sky Scout 2, which you see on this picture, is a first of its kind platform in that it's small, under 5.5 pounds, but still has interchangeable payloads. So one platform, multiple use cases, all in a compact size. That's kind of the unique selling point of the Sky Scout. So any questions anybody has for me, feel free to throw them out. Hey, David, I got muted. I'm unmuted now. Do you want me to take this slide too, or are y'all taking this one? Matt, I cannot hear anyone from the Impulse side. While they figure that out, I can go ahead and take this for
Oh,
sure.
I got it, John. But
Okay.
go ahead if you want. Well, let me go ahead. It's fine.
No problem. All right. So this is what our Whisper ground control looks like. And so one of the big parts that's one of the big things that separates us from the rest of our competition, I believe, is our easy use from our software. So when I was interviewing for this job, I was told that we're a software company that makes drones for specific applications. And it took me almost a full year to figure out what he meant by that. But the software is truly the biggest differentiator in the space. And that software to fly the drone, to fly the missions, how it incorporates and integrates other payloads, because you're marrying up a third-party sensor with a third-party gimbal with a third-party GPS, and you've got to get all that timed up perfectly because, I mean, you folks know better than anybody that centimeters and millimeters truly matter. And so this is Whisper ground control run by Whisper flight firmware. We run all of that internally, so we have full control over everything that we do. So this is planning a basic photogrammetry mission, and you more or less pull from the left and plan on the right. And so one of the first things that you do when you plan a mission with Whisper Systems is you choose your payload, and then you choose where you want to process that. So Pix4D is on the dropdown. Pix4D Matic and Mapper, because they want to see the gimbal angle in different formats in the EXIF data. And so you can pick your payload, pick your gimbal, and then the rest of the mission planning will pop up with the parameters best fit for that payload. And so on this one, we probably have the Sony ILX LR1 61 megapixel chosen. You hit that W up in the top left is kind of your main control button. This is our basic survey pattern. And then on the right, you can designate how fast you want to fly, how high you want to fly. It's going to give you your GSD based off of your height, your sensor, and your speed. And then you're ready to go. Again, it's meant to be very simple. We're very proud of the work that we've put in to do so.
Great. Thanks, John. All right, so back to the field. So just the workflow, if you're, on the project, a couple housekeeping items. First of all, you got to check your airspace. There are restrictions, obviously, but both on altitude and proximity to airports. And so Dave and Zach, I didn't mention, are both UAV certified FAA pilots 107, and they have apps that can tell you exactly where all of these encumbrances are. And like John was talking about, you define your polygon, you put your parameters in, and you're ready to go. And what's amazing is, to me, is how efficient this process is in terms of from the minute you get to the field to the time you're flying, it's like 15 minutes. This is a step we need to do when we get into orthophotogrammetry, which we'll talk about in a second. You need ground control points, GCPs. There is a standard under ASPRS. We'll speak to that later in this webinar, how that fits in. But you do need what we call checkpoints and also the GCPs. And that's going to take you a few minutes to get these laid out, depending on how many acres the site is and all that. And this particular site, I think, what was it, 6-7 acres, guys? It wasn't that much. We did 10 GCPs. Yeah. Took them a half hour maybe to drop these in and then put up some checkpoints. So once all that's ready to go, you literally say hit go. The UAV takes off. And if you're not familiar with it, when you see this for the first time, it's crazy with RTK, and it lands within a centimeter after where it took off. And you go pull the SD, you shut it down, pull the SD card out, and you're done. And in this particular flight, for the trajectory for the photogrammetry and the LiDAR, we ran both. We'll talk about that in a minute. We were talking about what, 6-10 minutes maybe a flight, and you're done. So just like Raptor and so forth, it's a little bit of pre-processing. So you have to take the data in to some software. In this case, it's PC Master, and you want to create. Well, first of all, you get your IMU data in there. If you're not familiar with the IMU, this is a inertial measurement unit. So when you have a UAV or anything that's moving in 3 axes, and you have, let's say, a laser pointing somewhere, well, you want to know absolute downrange where that laser really was based on these angles. And so this is all built in. Inertial Labs is also a partner within this process. And they are the IMU tech, and they're very, very advanced. And this is how we look at correcting for yaw, pitch, and roll. And it all gets back calculated into the spinal solution for the positioning of that actual return. So this is where we get here. And then you also create the point cloud, the LAS file, when it comes to the LiDAR, which is the standard format. Once you get the point cloud done, you have already now a very large range of outputs. You can do a digital terrain model. You can do a digital surface model. You can create the TIN, and then you can do a contour map as well. And this is all deliverables for more surveying activity, which when we were talking about earlier, what we found, what was really powerful for the Sioux guys was the photogrammetry. Now, I don't want to belittle the fact that you still may need all this information when you're going to regrade or whatnot, but you have it all within minutes, within extreme tolerances that you would need for an engineering decision on these on elevations as well as terrain and so forth. So what we did is, I'm not sure how many people are familiar with Mach 9 software, but Mach 9 is a pretty cool company, startup. They've been around a little while. We actually gave them this data set. This is the first time they've ever used their AI auto extraction for all of the features that we were able to pull out of the LiDAR imagery. And I don't remember the count, guys. What is it? It was 900 features they pulled out with AI that could be dropped right into CAD. And in this case, on the left, we dropped it into Esri. So all of this is all interchangeable. So Mach 9 software, you're looking at the first time they ever used drone data, because they were working on it for drones. We gave them the data and they helped us out. And all of these features were extracted. Of course, there are some adjustments you would have to make. And if I could zoom in, and I can't, this is just a still, the way Sahar put in the ArcGIS is to show you, but everything's dumped into ArcGIS, the light poles, everything. And if you zoom in, they don't look so cartoony, but this is just a slide to show you. But all those features were pulled right out of the LiDAR data and within a couple centimeters actually. So I'll go back to go here. So then we get into the other sensors. So now we're into what we call structure from motion, SFM. And in a second, I'll introduce Calvin Platt if he was able to get in, but I'll just start with how SFM works. So if you're not familiar with orthophotogrammetry, you've got a really nice high resolution camera, in this case, a 61 megapixel camera, the Sony. It's flying a trajectory with quite a bit of overlap. And every time it passes over a common part, a frame is common in many images, let's say, or many frames are common over a certain site. What the software will do, Pix4D specifically, it'll align these photos pretty well, and it'll identify by the pixel and an algorithm. It's like, I know what's around this pixel, I know the intensities, I know where this one is, ergo the other frames must be here. And it stacks, for lack of a better word, these frames together, and it creates this composite ortho mosaic. It also, because of the different angles of incidence of the reflected light, allows you to build a three-dimensional model, which I'll show you in a minute is mind-blowing where we're at with this. And on the left, you're seeing how we developed the TIN, which is a triangular integrated network. That's what we call your mesh. And you create first a coarse mesh, and then you get a dense mesh to create now a point cloud out of the photogrammetry and the pixels. And I believe, yeah, so I wanted to show you, I actually jumped ahead. I probably should have put Calvin a little ahead here, but I'll bring him in a second. But so this is the orthomosaic on the left, and I'll show you the resolution that you're going to get versus what you would on this project site from public Google Earth or whatever. And this is where it gets into the Sioux workflows now. We're starting to drill into this. I can, from 60 meters up, I can count the blades of grass, which is not what we do, but I can tell you that's a Bell South manhole. But when I click over to Google Earth, this is what you're going to have. So in 6 minutes, I had resolution that was able for me to actually see every utility feature that would be relevant, not under canopy, and relate this back to our underground data, which I'll show you in a minute. And so this is marks that we didn't put on, but you can in fact actually now map all your paint marks just the same as we're going to show you how we integrate the Raptor by just flying it. And then you can build a digital surface model from the photogrammetry just as you could with LiDAR. But I want to run through these frames to give you an idea of the detail and resolution from a camera system being converted into an LAS. And you can see the detail, every perturbance on the ground. But I'm going to show you something else that's more mind-blowing, because this was all new to us. I can see that we can zoom in and see the grout lines in the old tile floor sitting in where the whatever department was in the grocery store. So this is the resolution that we're going to get from these cameras and the capability we're going to have to create different maps. I am wondering if Pix4D slide, was it in here? I put a slide in for Calvin, but let me go on to Osprey View and how it.
Calvin's unmuted.
Yeah, Calvin, are you there?
I'm here. I was just
Yeah,
waiting for
okay,
you to give
good.
me the go ahead.
I had a lead-in slide for you, and I'm not sure what happened to it. But if you want to jump in, that's fine. Just introduce you. Calvin Platt he's national sales manager, I believe, or Pix4D. He's been helping us integrate and work with these processes and working with us as a reseller, getting started with this to help our customers. So I'll let Calvin, if you want to say a few words. I'm going to see if that slide is here, in fact, because
it's all good. I think
yeah, go ahead.
Showing the results as you've done here is far more valuable than seeing our logo sitting in front of folks.
Yes.
But yeah, we're excited to work with Impulse. I think that the subsurface results that Impulse technology provides, it pairs perfectly with Pix4D's data, right? And we historically are a photogrammetry company that focuses on drone collected data, the eye from the sky, if you will. So we can process results such as dense point clouds, which is really the basis of everything that we do, 3D textured meshes, digital surface models, and orthomosaics, of course, in 2D. So those are a lot of the consistent results from all of our solutions. What you might see as a most common solution to rely on for Pix4D workflows, again, for drone data processing, so collected from the sky, Pix4D Matic is our flagship and premier processing solution. It's desktop based, so locally processing. You plug your images in, your data files, and it will spit out those previously mentioned layers. So a DSM and ortho, 3D textured mesh, all based on the point cloud that's built from stitching the images together. So you might wonder then, how do I get the data points in from ImpulseRadar? We also have a solution, Pix4D Survey, where Pix4D Matic is a data processor. Pix4D Survey is a point cloud viewer as well as editor. So it has a number of different file types that it will accept as inputs, where you can import those in, overlay those inputs, and their files. LAS, LAZ files is a great example of the type of input that's accepted. You can overlay that data with your photogrammetry data. As long as everything is properly georeferenced, it will line up, with centimeter grade accuracy. And you can see both the subsurface results from ImpulseRadar as well as your above ground results processed with Pix4D overlaid onto the same result. One thing to note, and I'm only going to go in, a short while more here, Matt, but we actually are merging these two solutions, Pix4D Matic and Pix4D Survey, next year. They will all be still available separately, but all be available together under Pix4D Matic Pro. So very exciting results. We've been working on this for like 2 or 3 years now. But to have all of our processing workflows for desktop-based workflows, as well as all of our point cloud editing and analysis tools nested under one software solution, we're seeing that as a huge value add for our customer base. It's something that's been asked for a while. So the possibilities are only growing as far as using Pix4D alongside ImpulseRadar in 2026.
Excellent. Yeah, thank you, Calvin. I appreciate that. I wanted to just give a little bit of a, let's say, overview of how now we're going to integrate the Raptor data. So we're drilling down to what a consultant would do, an engineer. Matter of fact, we did have an engineering consultant help us out in this project with the CAD work. Noah Nelson, he used to work here and he helped us out. But I just want to show you the value of this now. So we've got just the ortho imagery itself. We've got Raptor data. So I can zoom in here and I can clearly read the sewer manhole. Now we didn't survey, we could have pulled the card out, but you can see the sewer line. Going back, the Raptor data or GPR data is just data. You don't know what facility it is. You have no idea. Their CAD person doesn't. If it was an unknown, for example, and it's just in the Raptor data, you don't know what it is. So you have to do some relational investigation. You could keep it an unknown if you can't figure it out, but by having the overlay of the high resolution imagery, you take a lot of ambiguity out of it, which you would never have heretofore. So keep in mind, the CAD operator has Osprey view as a layer, has the ortho imagery a layer, will have quality level D information as a layer, and will also have the field marks they picked up from a pipe cable locator. Just keep that all in mind. So everything's layered. So what I showed on the right hand is that we can read that water valve, from 60 meters up, but you could never do otherwise. And you can see our Raptor data clearly coming in and a couple other lines. Now the pick line in there, Dave, who's with us right here, he picked those through our own Condor software. But in CAD, they would normally just bring them. A lot of our customers for workflow will bring in the CAD, bring Osprey view in the CAD. Now they've got the ortho, and they'll just mark it out and line it out in CAD and not even our own Condor software. So this is some of the workflows that have helped out. Now this is where it gets really crazy, and this is not the latest presentation, but if you look at this is the coup de grace with Pix4D to me, okay? All of the data I just showed you could be visualized like this in 3D imagery. So if you've got a site and you haven't been there in 3 months, and you want to go back and look, and that's like or if you want to go back as if you were standing there at the day you surveyed and see it in 3D, the data we collected in 6 minutes is these data still. And you can create these 3D images from those data from the SFM. And it's if you walk the site. And I can tell you from a former SU consultant, having this information available to say, hey guys, did we pick up that, water distribution system right here? And did we miss anything? Well, guess what? I can walk you back to that site in 3D 2 years from now, or as long as you want to archive the data. And I can go back and do this kind of stuff. I mean, I like I said, this was exciting for us because we're underground people, but to be able to do this and stitch this together in terms of a workflow was just tremendous. And I wish I had had this in my days as a supervisor. And I mean that this isn't a sales thing. This is just a workflow thing, and having struggled for real in the field. So this is Noah as an EIT, worked for an engineering firm. I said, just do this as if you're a consultant, which you are, and go through your workflow. So he brought in Osprey View, the ortho, into Civil 3D, and he worked through it and lined everything out as if he would do it. And you can see the value of the Osprey View. You can see the value of the ortho imagery. He used all of it, and he was able to build his deliverable map, going back to this process. What I like to point out on some of these too is the lines that were put on by the blue paint as usual were wrong. This is mismarked, and you can clearly see that in the Osprey View. And just being able to read these valves and superimpose. So this is his deliverables, and this is what he would have as a final deliverable for his CAD investigation. So this is what we learned and how it could be integrated. Now, just a little bit on accuracy, because obviously there's a standard in the ASE 3822. It's 0.2 feet, I believe. 0.2 feet is the standard for accuracy under the SU standard. So we wanted to make sure that all these data okay, is it useful? Does it meet the ASE 38 standard? Well, guess what? There's a standard under ASPRS, American Society of Photogrammetry Remote Sensing, and how to manage accuracy and document it. Because remember, guys, we're not PLSs sitting in this room, but if you're an engineering firm and all that, you're stamping these drawings. So it's important to have these data verified. And I love this slide, because the guru and father of SU is James Onspach. I think anybody in the SU industry knows who he is. He's a great guy, and I've been a friend of his for many, many years. And he likes to talk about accuracy and precision. And this was in their own, this is from one of their references. And it just shows you the difference between accuracy and precision and how that can be confused and what they really mean. Obviously, you can see pictorially what it means. So the standard does have accuracy standards for the size of the site. Now, the size of our site was way below where they start the accuracy standards. So I believe they wanted what we call 25 checkpoints, I'll speak to in just a second. So what a checkpoint is you saw that we put the GCPs out. So in the GCP, in the workflows for Pix4D, which is beautiful, it actually finds the GCPs for you. Like, you've got hundreds and hundreds of photos. Well, you're not going to want to scroll through all those and say, where's my GCPs? It's really smart, and it says, well, here's your GCPs, and it panels them for you. And what you do with a GCP is you're going to make sure that your survey mark is pulled into the center of that GCP. So you zoom in on them. I don't have a picture of it. You zoom in on it to a high degree, and you can manually adjust and shift that point into the GCP, and boom, you've got that positioning geo-rectified, let's say, from real to what the imagery was. As a further check, we have what we call checkpoints, and we did 10 checkpoints. So Dave and Zach walked around and went to features that you can pull out in the photograph or on the orthomosaic and say, hey, how far off are we? And this is all from the ASPRS standard. So they do a root mean square error calculation, which is basic math, on the 10 checkpoints. And we came out with a total RMSE error of 0.0316 meters, 3 centimeters, and it's half of the accuracy required for the ASC 38, which is really 6 centimeters. So over the 6 acres in 10 minutes, with a few checkpoints, all these data just went right into the accuracy standards that we need for the entire project. So I'm going to conclude there in terms of how, from A to Z, how we approach this as a consultant. We can see that the platforms, allow these advanced processes and collecting of data, picking up paint marks, utility features. We validated the workflows and the efficiency of this. I mean, it's here today, is where I see it now, as something that, paper is gone, and having these digital twin records is the future. So there's a great advantage of this for the SUE process. And now UAVs and positioning and all that, when I first got into the SUE industry, GPS was just coming to the fore, and you couldn't find a good GPS system for less than $40,000. Now you're looking at, let's just say below 10,000, below 5 in many cases, like Emwoods that we sell. But there are challenges. There's no perfect, there's no panacea. You've got tree canopy, if you notice in that aerial imagery. Well, what if you got paint marks in the tree canopy? Well, you're going to still go in there and pick those up. I can tell you this, you can put an Emwood, what's the little RX system on your phone, use Pix4D Matic, Pix4D Catch, and you can scan that area and pick those up. And, we didn't even get into that, maybe for another time. But you could still go in there with a rod and a total station and pick those up as well. You got airspace restrictions, and by the way, we were okay flying over that site, but we really shouldn't be flying over the highway, the busy highway off to the left or right. So we had to make sure that our polygon didn't infringe over those areas, because we didn't have control of those areas. So these are just some of the things. Data sets are big, full disclosure. I went and bought an Alienware computer, and so did Zach. So we can process quickly, a much more robust computer on the GPU. So these were some of the things that we learned, but it was a beautiful, let's say, experience from being a consultant, bringing all this tech in to try to bring us up to date on the other side of the planet that we don't really specialize in. We're the underground guys, but just to see it come in. So I just want to thank everybody for that participated, particularly Sahar out in Oregon. She's a wonderful person. We really enjoyed working with her, and I want to thank guys at Whisper, Pix4D for their support, Mach 9. We are an Esri partner, so we've been working with Esri for a long time. So I appreciate it, and we'll certainly take any questions that you all have. We'll do 5 minutes of Q&A.
Yeah, so at this point, we'll go ahead and open up the floor. If you guys have questions, feel free to type those into the chat, and then we can just answer them verbally as they come. But yeah, as Matt said, thanks for your time. If anybody does want further information, we are certainly more than happy to set up Teams meetings or any follow-up phone calls if you guys want to get into specifics of how you can bring these workflows into your company and help with your processes. We're certainly happy to do that. Zach, did you have anything else you wanted to add?
Mm-hmm. Yeah, Anthony, appreciate the couple questions in there about ENSS accuracies. We got a question from Manuel Playa. Sorry about that. What is the max depth that you can reach with the Raptor GPR? It's pretty dependent on local soil conditions. So GPR functions best, can penetrate deepest in resistive soils. Conductivity is kind of the enemy of depth penetration. Down in Florida, we get very resistive soils, very low conductivity. We can see 10, 12, 15 feet in some places. In conductive soils, for example, like Denver and Phoenix, Arizona, we might be seeing 3 to 4 feet. So it can vary very, very greatly, different soils.
Well, let me add to that. Even in soil conditions, actually, let me just clarify, it's also frequency dependent. So the Raptor 450 is geared to utilities. But of course, with GPR in those same really good soils, we can see 30, 40 meters with the right antenna, but it's not the same antenna you would use for utilities because of resolution. But I also want to add that we have many raptors out there. And what's remarkable is even in really poor soil conditions, the value that you get out of these super congested areas that you would never be able to still get pushing a 2D radar. And I mean that. And as much as we have the #1 selling radar system, the pinpointer for utilities, if you're got 5 blocks in downtown, wherever, even if the soils aren't ideal, it's amazing how many unknowns our customers find still using the radar. And also it's a really good trench imager. In the worst case scenario, you can actually identify, you can't directly detect utility, but you can certainly see the trenches that you can still see with a 2D radar, but not like you can with the image of a trench. What was the other?
Got one more question from Randy. With the GPR data acquisition speeds upwards of 50 miles an hour, how often is the GNSS receiver collecting a point?
And they're all at 1 hertz. GPS updates 1 hertz. So obviously the slower you go or the faster you go, you know, you'll have some, but I mean, that's a great question because what we do in between GPS points is we interpolate. You're usually run a straight line with a vehicle. So we're still in between those points. We're still centimeter accurate, a few centimeters. It's not centimeter.
What's happening there is we have a wheel encoder on the back left tire of the vehicle. Usually we have it set to collect a GPR trace every 4 centimeters. So it is recording the distance scan.
That's correct. Yeah. And then you'll just ascribe, we ascribe a GPS point to those points, and you can run in time mode also, but anyway.
We got one more question from Alejandro Padron. It's good to hear from you again, Alejandro. How are you able to do the fusion and ensure the proper positioning between the GPR data and the point cloud? Right?
Oh, that's no problem because you have #1, you've got GCPs that verify its position within itself. And then with the Raptor data, we also have a way to we can verify the positioning.
Yeah, and actually, when we lay these layers of data on top of one another, I mean, the LiDAR and photogrammetry are both going to pick up surface features very well. We can actually see them matching up, right? The Raptor is using RTK for the positioning, and then the LiDAR and photogrammetry are using both GCPs and post-process kinematics from local core stations.
Well, plus you can put markers in the Raptor data in the field if you wish. If you go over a known or an object that's surveyed in, you can put that survey object in the data, and it lives with the data. So you can do an alignment that way as a QC process. So all those workflows are available within our Raptor software in Talon. You can go out and put a rod out and do the same thing. You can put data in down to a NATS rear end with a total station and put those markers in the Raptor data.
And another thing, whether you put surface markers in or not, things like valve covers and manhole covers show up quite distinct in the radar data. So you can also match those up with the above ground imagery.
Okay, got another one from Randy. Now could you incorporate the photogrammetry data to the GPR data, i.e. XYZs? I'm not sure I quite understand. Maybe if you could elaborate a little bit.
You're talking about the elevation versus depth, or?
Yeah, that's stuff. You could elaborate on that just a little bit.
GPR data. I think you just answered that actually.
Yeah, I think talking about the surface features.
Right.
Like
Yeah.
valves,
I mean, yes.
Valves and
Now on the Z end, that's a great question because orthophotogrammetry and all that is not sub-centimeter on elevation. I think we were looking at what, 4 or 5 centimeters, 4 centimeters on elevation. I can't remember how we determined that. We had some knowns or something.
Yeah.
So your vertical elevation is not near as tight as your XY. So that's a good question. Is maybe where he's getting at. Now, when it comes to depths with radar, those are also estimations based on our algorithms and how we calculate velocities of the soil. If you notice in the data, there's no hyperbolas. We get rid of those. It's called a migration, and migration algorithm is a very robust algorithm that takes a hyperbola. And in our case, it's a true 3D. So if you had a point diffractor, it's going to be a dome it's not going to just be a hyperbola, it's going to be a dome of hyperbolas around an object. So what migration is we actually have a good velocity. We actually collapse that energy back to where we know mathematically it really came from, because it came from here, not out here. So when you get an ultimate solution in migration to really make that image really crisp, that means we've got a velocity solution that's really good. And it's still just an estimate. So even at best on Raptor data, it's going to be within 10%. We will never represent that it's an absolute depth. And keep in mind, those are depths to the top of a pipe, not to the bottom or the invert. So, you know, when you get into the, you got to be careful with that. And also one note on an EM locator, the depth, if you do electronic depths from an EM locator, that's to the conductor. You don't know really where that depth is. It's going to be in the center sometimes of a conductor. If it's tracer wire, it could be a good foot off, 2 off.
So we got.
Yeah, we'll take one more.
Can you provide an estimation of the height and elevation above the surface for a GPR survey combined with UAV? We are not doing that currently. And once you, Matt, you want to talk about GPR on a UAV a little bit?
You know, it has its value, but in the SU industry, I would say not. It's smoke and mirrors. I hate to say it. So if anybody's representing, you could fly a corridor with a GPR. I'm sorry, as a manufacturer, I think it's, I don't know what the best word to say that's polite, but I would, but, you know, in its simple physics, you have an airborne radar system that's actually designed to be ground coupled. Now it's airborne. And depending on the surface conditions, particularly most corridors, they're going to be reasonably conductive. They're not going to be perfect. You're going to get a high percentage of the energy from the radar system bouncing off the surface. And I've seen LinkedIn videos. I know some, I won't name any names, but a very respected expert in GPR ripped into some people that had a LinkedIn post, and they deserved it, of what they were trying to do by suspending a GPR antenna over some pretty crappy ground. In ideal conditions over, let's say, Ocala, Florida sands or a sand dune, sure, it'll work. I think the primary focus for an airborne GPR would be snow and ice investigations and maybe some bathymetry. Those are proven. But when you get into utility mapping, I would say you're wasting your time for the most part.
Yeah, just so you guys are aware, our tow behind Raptor system is sitting about 1.5 inches off the ground, right? So it is ground coupled.
Yeah, all GPR systems are designed to be ground coupled. It doesn't mean they can't work. But the conditions, the ground conditions have to be really perfect to get penetration from altitude.
We got one more from Pix. Good to see you, man.
All right, we'll wrap up with this.
From a SU perspective, what will the final deliverable be to your client after consolidating all the information? A CAD file? Question mark.
Yeah, you know, the deliverable at the end of the day for a SU provider is a map.
Yeah.
And you know, my experience, I always used to say the client doesn't care. You know, we care about our workflows and our technology and our processes, because that's what we do. We have to be as efficient and as accurate as we can, because you got to stamp the drawing. But at the end of the day, you're providing your client a roadmap to mitigate relocations of utilities and a plan.
One of the most helpful aspects of this workflow was that when we fly this with different payloads, it's almost creating a base topo for us to use in reference to the underground data in order to designate utility types.
Yeah.
And also to further answer that question, Pix, yeah, a lot of our clients are generating CAD files. Sometimes the deliverable is just a 2D map. If that's what the end user wants, then that could be.
I will not name names, and I'll wrap up with somebody. I won't name a name, saying he's worked with airborne GPR data and it's crap. I appreciate. I'm not going to name names. Maybe y'all can.
I think everyone can see.
Yeah. But
Put your name. I'm so sorry. The balls. Step by step on how to connect a Leica total station Raptor.
Well, we'll take care of that offline.
Yeah. Reach out, just somehow reach out to us, maybe fill out an inquiry on the website, and our Swedish colleagues can certainly help with that. They've got lots of experience with Leica total station.
All right, well, we want to thank everybody. Really appreciate your time, and we're always available offline.